In the summer of 2024, something happened that shouldn't have been possible. An object from interstellar space, a visitor from beyond our solar system, flew closer to the sun than Mercury ever gets, and instead of vaporizing into a cloud of gas and dust like every model predicted it would, it just didn't. 3I Atlas, only the third confirmed interstellar object we've ever detected, broke the rules. And when something breaks the rules in astronomy, it means the rules themselves might need rewriting. To understand why this matters, we need to go back further than you might expect, not just to 2024, but to 2017, when we first realized we weren't alone in the solar system. I don't mean aliens, I mean visitors. Objects passing through our cosmic neighborhood that didn't originate here at all. Before 2017, the idea of interstellar objects was purely theoretical. Astronomers knew they had to exist, simple mathematics demanded it. When star systems form their messy, chaotic affairs, material gets flung outward, ejected into the void between stars. Over billions of years, the galaxy should have filled with these cosmic refugees, wandering the darkness between solar systems. But theory is one thing. Actually finding one of these objects, that's something else entirely. The problem is speed and timing. Interstellar objects move fast, tens of kilometers per second, and they don't stick around. They fall through our solar system on hyperbolic trajectories, meaning they're not bound by the sun's gravity. They're just passing through, and we have only a brief window to spot them before they vanish back into the cosmic darkness. For most of human history, we simply didn't have the technology to catch them in the act. That changed on October 19, 2017, when a telescope in Hawaii called Pan-STARRS detected something odd. At first, astronomers thought it was a comet, then maybe an asteroid. But when they calculated its trajectory, they realized it was moving too fast, way too fast. The object, later named ʻOumuamua, Hawaiian for scout or messenger, was the first confirmed interstellar visitor, and it was already on its way out. ʻOumuamua raised more questions than it answered. It was strangely elongated, tumbling through space, and it appeared to be accelerating in ways that couldn't be explained by gravity alone. Some scientists suggested it was outgassing like a comet, but no one could detect any gas. Others, more speculatively, wondered if it might be artificial. The truth is, we still don't know exactly what ʻOumuamua was, because by the time we realized what we were looking at, it was too late to get a good look. Then came 2I Borisov in 2019, the second confirmed interstellar object. Unlike ʻOumuamua, Borisov behaved exactly like we expected a comet to behave. It had a visible coma, it outgassed, it followed predictable patterns. In a way, Borisov was reassuring. It suggested that most interstellar objects would be comprehensible, that ʻOumuamua might have been an anomaly. Scientists breathed a collective sigh of relief. The universe made sense again. And then 3I Atlas showed up. The discovery of 3I Atlas came in February 2024, picked up by the Atlas Survey System, the same network that monitors for near-Earth asteroids and comets. Early observations immediately flagged something unusual about its orbit. The eccentricity was off the charts, suggesting another hyperbolic trajectory. Within days, astronomers around the world had confirmed it. This was the third interstellar object, and unlike the previous two, we had caught it early. Very early. This was the golden scenario astronomers had been hoping for since ʻOumuamua. We had time, months potentially, to study this object as it made its way through the inner solar system. Observatories were immediately retasked. Proposals for observation time flooded in. Everyone wanted a piece of this. The initial characterization suggested 3I Atlas was relatively small, somewhere between 50 and 200 meters across, though that estimate would change, and it appeared to have properties similar to a comet. There were signs of a faint coma, suggesting it was releasing material. This made sense. As objects approach the sun, they heat up. Volatile materials, water ice, carbon dioxide, methane, begin to sublimate, turning directly from solid to gas. This is what creates a comet's distinctive tail. By March, the orbit had been refined enough to make a startling prediction. 3I Atlas was going to pass extremely close to the sun, closer than Mercury, closer than many sun-grazing comets that routinely disintegrate. The perihelion, the closest approach to the sun, was calculated to occur in late July 2024 at a distance of just 0.15 astronomical units, For context, Mercury orbits at about 0.39 AU. This object was going to get seriously close. This is where things got interesting because there's a well-established pattern in astronomy. Small comets that pass this close to the sun don't survive. They fragment, they vaporize, they become diffuse clouds of gas. The heat is simply too intense. The physics are unforgiving. Water ice doesn't just melt at these distances, it explosively vaporizes. Dust grains embedded in the ice are released suddenly, and the structural integrity of the nucleus collapses. We've watched it happen dozens of times with sun-grazing comets detected by solar observatories. Let's talk about what actually happens when a comet approaches the sun, because the details matter here. A comet isn't just a solid ball of ice and rock. It's more like a loosely packed snowball mixed with dirt, frozen gases, and organic compounds, what astronomers charmingly call a dirty snowball. The structure is porous, fragile, held together by weak gravitational forces and the frozen binding of ice. As a comet approaches the sun, radiation heats the surface. This isn't a gentle warming. We're talking about intense solar radiation that can raise surface temperatures to several hundred degrees Celsius. The ices don't get a chance to melt into liquid. They sublimate directly into gas. This creates pressure beneath the surface, and gas begins to vent outward, carrying dust with it. This is what forms the coma, the hazy cloud around the nucleus, and eventually the tail. But here's the critical part. This process is violent and destabilizing. As gas vents, it removes material from the nucleus. The comet is literally losing mass. And because the structure is so fragile, this mass loss can trigger catastrophic breakup. Think of it like a sandcastle being eroded by waves. Once you remove enough supporting material, the whole thing collapses. For small comets passing within 0.2 AU of the sun, this breakup is almost inevitable. We've documented it repeatedly. The comet fragments into pieces, those pieces fragment further, and eventually you're left with nothing but a dispersing cloud of dust and gas. The sun-grazing comets detected by SOHO, the Solar and Heliospheric Observatory, routinely disappear as they round the sun. We see them approach, and then nothing. So when astronomers calculated that 3I Atlas would pass at 0.15 AU, the expectation was clear. This object would not survive. Papers were written. Observation campaigns were planned to watch the breakup in detail. This was going to be a fantastic opportunity to study the destruction of an interstellar object in real time, to analyze its composition as it vaporized, to learn what it was made of by watching it die. The predictions were confident, models were run and rerun, the consensus was overwhelming. 3I Atlas would fragment, probably in the weeks leading up to perihelion, certainly during or shortly after. Some astronomers predicted we might see multiple fragmentation events as the nucleus broke into chunks, each chunk subsequently breaking down further. There were a few dissenting voices, there always are in science, suggesting that if the object was mostly rocky rather than icy, or if it had an unusually strong internal structure, it might survive. But these were minority opinions. The data suggested significant outgassing, which meant ices were present and actively sublimating. Everything pointed toward a fragile object on a collision course with solar destruction. Telescopes around the world were positioned, space-based observatories adjusted their schedules. The James Webb Space Telescope was allocated time to observe the perihelion passage and its aftermath. This was going to be spectacular. July arrived. 3I Atlas approached perihelion. Observers watched, instruments ready, waiting for the telltale signs of fragmentation, a sudden brightening, a spreading of light indicating multiple fragments, a change in the spectroscopic signature, and nothing happened. The object rounded the sun, passed through perihelion on July 28th, and emerged on the other side intact. Not just intact, seemingly unchanged. The light curve showed no signs of fragmentation. The coma remained consistent. Spectroscopic analysis indicated the same composition before and after. It was as if the object had simply ignored the sun's attempt to tear it apart. The initial reaction in the astronomical community was disbelief, followed quickly by frantic rechecking of data. Had the size estimate been wrong? Was the object larger than calculated, giving it more structural integrity? Revised estimates suggested no. If anything, it might have been slightly smaller than initially thought. Had the composition been misidentified? Perhaps it wasn't icy at all, but purely rocky? But That didn't explain the coma, the outgassing that had been consistently observed. Rocky objects don't produce coma. Had the perihelion distance been miscalculated? Absolutely not. Orbital mechanics is one of the most precise sciences we have. Multiple independent observations confirmed the trajectory. 3I Atlas had definitely passed at 0.15 AU. As 3I Atlas receded from the Sun through August and September, the observations continued and the mystery deepened. The object was still there, still outgassing, still very much a coherent entity. By October, papers were being rapidly drafted, conferences were being held, and the question everyone was asking was the same: how? One early hypothesis focused on composition. Maybe 3I Atlas was made of materials we don't commonly see in solar system comets. Interstellar space is cold, really cold, and objects forming in different stellar environments might incorporate different ices, different minerals, different structural elements. Perhaps it contained refractory materials, substances with very high melting and sublimation points that gave it unexpected durability. Some researchers pointed to the possibility of a protective crust. If the outer layer of the object had already lost its volatiles in a previous encounter with another star, it might have formed a hardened, non-volatile shell that protected the interior. Think of it like a heat shield on a spacecraft, a sacrificial layer that ablates and protects what's underneath. Others suggested tensile strength might be the answer. Most comets are loosely bound rubble piles, but what if interstellar objects, formed under different conditions or subjected to different processes during their eons-long journey through space, had undergone some kind of sintering or compression that made them fundamentally stronger than solar system comets? There was also the possibility of internal structure. Perhaps 3I Atlas wasn't a uniform dirty snowball but had a rocky core surrounded by icy layers, and that core provided structural support that prevented catastrophic fragmentation even as the outer layers vaporized. So why didn't 3I Atlas burn up? The honest answer, as of now, is that we don't know for certain, but the most likely explanation, the one that's gaining consensus among researchers, is that we fundamentally underestimated the diversity of small bodies in the galaxy. Our models for cometary behavior are based almost entirely on solar system comets, objects that formed in our particular stellar nebula, orbited our particular sun, and evolved under our particular conditions. We've been extrapolating from a sample size that, cosmically speaking, is incredibly limited. It's like trying to understand all of Earth's geology by studying a single valley. 3I Atlas came from somewhere else. It formed around a different star, possibly billions of years ago. The chemical composition of that protoplanetary disk might have been different. The temperature gradients might have been different. The formation dynamics might have been different. And then, after being ejected, it spent potentially millions or billions of years in interstellar space, subjected to cosmic rays, to impacts from interstellar dust, to temperatures near absolute zero. All of these factors could have created an object that looks superficially like a solar system comet. It outgasses, it has volatiles, it develops a coma, but is fundamentally different in ways we're only beginning to understand. The survival of 3I Atlas suggests that our category of comet is too narrow, too parochial. There are structures, compositions, and formation histories we simply haven't encountered yet. There's also a timing element that matters. We've only been capable of detecting interstellar objects for 7 years. We've confirmed exactly 3. That's not a representative sample of anything. For all we know, objects like 3I Atlas, survivors of close solar passages, might be common, and we just haven't seen enough examples to recognize the pattern. The fragile, easily destroyed comets might be the anomaly, not the norm. The other factor is observational bias. We're much more likely to detect interstellar objects when they're near the sun because that's when they're brightest and most active. But that also means we're catching them at their most extreme conditions. We're testing them to destruction by default. The survivors, the tough ones, the anomalies, those are the ones that stick around long enough for detailed study. We might be systematically missing the fragile interstellar objects because they disintegrate before we get a good look. 3I Atlas is still out there now, heading back into the outer solar system and eventually into interstellar space. In a few decades, it will be beyond the reach of our telescopes, just another wanderer in the galactic dark. But what it's left behind is more valuable than the object itself. a reminder that the universe is larger and stranger than our models suggest. Every time we think we understand how things work, how planets form, how stars die, how comets behave, the universe shows us an exception, and exceptions are where we learn. They're the data points that don't fit the curve, the observations that make us reconsider our assumptions. The survival of 3I Atlas tells us that interstellar space is not a uniform void filled with uniform objects, it's diverse. Things form differently out there. They survive differently, they behave differently, and our task as a species newly capable of detecting these visitors is to expand our understanding to accommodate that diversity. We'll see more interstellar objects. The Vera Rubin Observatory currently coming online is expected to detect several per year. Each one will teach us something new about the galaxy beyond our solar system. Some will behave as we expect. Some, like 3I Atlas, will surprise us. And that's exactly as it should be. Science advances not by confirming what we already believe, but by encountering what we didn't expect. 3. Atlas didn't burn up because it was tougher, stranger, and more resilient than we predicted. It survived to remind us that the galaxy is full of objects we've never seen, formed under conditions we've never studied, carrying stories we've only begun to read. The scientists aren't just stunned, they're listening.